We experience the world in 3 dimensions, but the media we consume is overwhelmingly flat. When a 2-dimensional plane shifts, our brains instantly calculate the emerging volume and geometry. Teaching a computer to do this, inferring 3D depth from a single static image, is a geometrically ill-posed problem. A camera compresses the physical world onto a flat XY pixel grid, erasing the Z-axis entirely. Think of a human trying to catch a baseball with one eye closed. Without binocular disparity to measure distance, the brain relies entirely on learned visual priors: the size of the ball, the angle of the shadows, and how it occludes background objects. Replicating that specific capability is critical for hardware. Autonomous vehicles and robotics rely entirely on accurate 3D scene reconstruction to navigate spaces without crashing into unseen obstacles. To solve this, engineers have poured resources into bespoke convolutional neural networks and massive transformer models designed specifically to predict depth. Yet these specific discriminative models frequently fail. Because their knowledge is restricted to the specific data they saw during training, they struggle to map distances when confronted with unfamiliar room layouts or novel environments. Memorizing a training environment is not enough. True robotic autonomy requires a visual system that intuitively understands universal physical relationships, regardless of where it is deployed. A team of researchers recently introduced Marigold. They proposed a counterintuitive thesis. The solution to this highly specific discriminative depth task actually lies hidden inside generative image models. Their goal is to achieve zero-shot generalization. In computer vision, this means a model can perform accurately on entirely new types of data it has never encountered before without needing retraining. Traditional depth estimators are constrained by narrow, highly specialized datasets. Stable Diffusion, on the other hand, was trained on billions of diverse images, spanning nearly every conceivable visual concept on the internet. Imagine a master painter. Even if their sole job is to produce colorful 2-dimensional landscapes, doing that job perfectly requires a flawless internalized understanding of light, shadow, perspective, and relative distance. By repurposing an image generator, researchers bypass the narrow constraints of traditional depth models. They are tapping into a vast, pre-existing database of physical reality. This diagram illustrates the core mechanism of a diffusion model. During training, the system iteratively adds Gaussian noise to a clean image until it is entirely degraded. It then learns the exact mathematical steps to reverse the process, denoising the static back into a coherent visual structure. To harness this engine for depth estimation, the Marigold architecture intentionally freezes the core generative weights of Stable Diffusion. They lock down the model's universal visual knowledge so it cannot be overwritten or forgotten. This processing doesn't happen at the pixel level. It occurs in the latent space, a highly compressed mathematical environment where the model maps and stores the deep relationships between visual concepts. The researchers only modify and fine-tune these specific latent pathways. Instead of asking the model to decode its latent map into RGB color values, they train it to output a grayscale distance representation. Because the heavy lifting of scene comprehension is already done by the frozen weights, this fine-tuning process is highly efficient. It requires only a few days of processing on a single standard GPU. They are not teaching the model how to perceive depth from scratch. They are extracting the 3D geometry the model had to learn while practicing 2D generation. This UNet architecture is Marigold's structural backbone. An RGB image enters the encoder, compressing into a dense mathematical representation at the bottleneck. Marigold injects raw image features directly into the network through cross-attention conditioning. Inside the right-side Dakota, the model performs iterative denoising, guided by these injected features, to construct an accurate depth map. Traditional CNNs calculate depth in a single, rigid forward pass, but the diffusion approach relies on multiple iterative refinement steps, constantly checking its geometry against the original image. The UNet structure allows the abstract geometric understanding in the diffusion prior to align flawlessly with the exact pixel coordinates of the target image. Training any depth estimator requires data, but capturing clean, accurate 3D data in the real world is notoriously difficult. Sensors suffer from noise, transparent surfaces confuse lasers, and varied lighting corrupts the measurements. The researchers made a highly pragmatic decision. They trained Marigold entirely on synthetic, computer-generated datasets like HyperSim and Virtual Kitty. Usually, this triggers the sim-to-real gap. Models trained in pristine, video game-like environments often fail when deployed in the messy, unpredictable physics of the real world. The primary issue is absolute scale. If you show an AI a picture of a car without any background context, it cannot determine if it is looking at a 2-inch toy on a table or a 2-ton vehicle in a parking lot. To close the sim-to-real gap, Marigold predicts affine and variant depth. D star equals S times D plus T. Instead of exact metrics, it predicts depth up to an unknown scale, S, and shift, T. It focuses strictly on relative ordering, knowing the hood is definitively closer than the windshield, regardless of absolute size. Affine invariance removes scale confusion entirely. By letting go of absolute metrics, the model can take knowledge learned in a synthetic simulation and map it seamlessly onto complex, unmeasured reality. To prove the efficacy of this method, the team tested Marigold against highly optimized discriminative models using completely unseen, real-world datasets that none of the models had trained on. This chart visualizes the zero-shot generalization results. By leaning on the Stable Diffusion backbone, Marigold achieved over a 20% increase in accuracy compared to the previous state-of-the-art. The traditional depth models suffered failures in edge cases, unfamiliar architectural layouts, highly detailed foreground objects, and extreme perspectives that fell outside their specific training parameters. In those exact same edge cases, Marigold generated clean, artifact-free depth maps. The robust visual knowledge embedded inside a generative model mathematically outperforms bespoke single-task architectures when forcing a system to interpret the unknown. There is a notable trade-off. The iterative, multi-step denoising process that gives diffusion models their accuracy also makes them inherently slow to run compared to single-pass networks. Furthermore, predicting relative, affine invariant depth is perfect for understanding the shape of a scene, but it remains insufficient for industrial robotics tasks that require exact metric measurements to grasp physical objects. Future research will likely focus on distilling the massive intelligence of this diffusion model into a faster feed-forward network, optimized to run on edge hardware. What Marigold proves is that diffusion models are highly capable scene-understanding engines. They possess a latent geometric logic that can be extracted and applied to objective measurement. It also demonstrates that the sim-to-real gap is solvable. Affine invariant training on purely synthetic data successfully equips AI for the physical world. The 20% performance leap demonstrates that foundational generative models provide a more robust starting point for depth estimation than task-specific architectures. The same logic used to synthesize a scene can be precisely inverted to reconstruct its geometry.